Hello students. So let's go for quick revision for harmonic oscillator. In the JAM examination mainly, from the harmonic oscillator, there is straightforward question. So you have to just remember what is eigenvalue, what is eigenfunction, and what is the profile of eigenfunction mainly. So, but before that, you have to remember one basic integration, and that integration is gamma integral. So first you have to practice this particular integration, minus infinity to plus infinity xn e to the power minus alpha x square dx. So this integration is very important, and if n is odd, then obviously this integration, this I is equal to 0. But if n is even, so if n is even, then you can go for this integration 2 times 0 to infinity xn e to the power minus alpha x square dx. And this integration will be 2 into, this is due to this 0 to infinity, but this particular integration is 1 upon 2 into 1 upon alpha to the power n plus 1 by 2 and gamma n plus 1 by 2. So this is very important tool for solving the harmonic oscillator. Now you have to focus what is the energy eigenvalue and what is the energy eigenfunction. So in our operator method, we can write Hn is equal to n plus half h cut omega n kit, and n can we go from 0, 1, 2, 3 and so on. And here is the profile of ground state. You can say 0 kit, or which is equivalent as phi naught x, and this is 1 kit or equivalent to phi 1 x. The corresponding eigenvalue for ground state is h cut omega by 2, and here 3 by 2 h cut omega. And you should also remember the turning point. What is the turning point? The turning point is the point where the total energy is equal to potential energy. There is not any kinetic energy. So in term of energy, you can write the turning point, and this turning point is basically, I think, root under, you can also calculate this turning point. E is equal to half m omega square x square. So this will be 2e upon m omega square root under is your x naught. This is your turning point because total energy is potential energy. And you should also remember the functional form of at least ground state and first excited state. So functional form of ground state is just a very famous Gaussian wave function, and this will be m omega upon pi h cut to the power 1 by 4 e to the power minus xi square by 2. And what is value of xi? You can also remember the value of xi is equal to m omega upon h cut root under into x. So in a complete form, you can remember ground state phi naught is m omega upon pi h cut 1 by 4 e to the power minus m omega x square upon 2h cut. And you should also remember the functional form of potential. We are just writing all these things for functional form of potential. Vx is equal to half m omega square x square. If omega is going to change or this number is going to change, you have to change here normalization also and as well as this functional form also. So this is very important, that which type of potential is given. In general, it is given a trend that they will just write this thing into different form, and you have to write the wave function into this form. So this is very important, and similarly you have to change this particular energy eigenvalue, and you should remember the harmonic oscillator energy eigenvalue is function of omega, and this omega is comparable to this particular potential. So this is very important. Another thing is that you have to also remember phi 1 xi, and this value is again m omega upon pi h cat to the power 1 by 4. You can just go for 1 by root 2, 2 xi e to the power minus xi square by 2. So this is the thing for the first excited state. You should remember also this one, because sometime they will give you that any state can be function of ground state, the superposition of ground state and first excited state. And when you need to calculate the expectation value of x or x square, then obviously this particular thing is very important. Otherwise, you can just use this ncat and you can solve the problem into Dirac notation for the energy and all other thing. So this is very important, and you have to also calculate and just check that expectation value of x in any energy eigenstate. I'm just talking about any energy eigenstate, n x n is equal to 0, because you can see this potential is symmetric about x is equal to 0. And you have to also remember expectation value of x square, and the expectation value of x square is equal to h cut upon 2m omega 2n plus 1. So this two thing you have to remember. And similarly, you can also calculate px. The expectation value of px will be also 0, and you can also calculate the expectation value of px square. Now, sometime they will give you the problem mainly based on semi-infinite potential. So when they will give the problem for semi-infinite potential, so I am just using this space for semi-infinite parabolic potential. So this is your infinite potential, and this is parabolic. Here is infinite, and this is half m omega square x square. Then your energy, the ground, then only n is equal to 1, 3, 5, and so on are the allowed value, because we have to check our wave function must be vanish at the x is equal to 0, because there is infinite potential. So the ground state wave function, it's something like this for this particular potential. So this is for n is equal to 1. So for n is equal to 1, we have ground state. So we can write the easy ground state is E1, and that will be 3 by 2 h cut omega. The EF is the first excited state is equal to E3, that will be 7 by 2 h cut omega. But here the ground state, if you have both side parabolic exact harmonic oscillator, then your ground state is h cut omega by 2, and the first excited state is 3 by 2 h cut omega, and you can have next excited state is 5 by 2 h cut omega. So this is the thing you have to remember for the harmonic oscillator. The problem will be come more or less from all this concept, but thing is that how you are using the particular gamma integration, and how you can use this particular ncat for the energy and all other thing. So just go and revise this thing from your notes, but focus on all these particular problem. And I also request you that the operator method is not for the JAM exam. This is for maybe for TIFR exam, just examination. But in the JAM exam, they will just give you straightforward problem based on integration and all other thing. So the student, you can just revise it, and I am sure that harmonic oscillator question will be just a straightforward question, but you have to also remember little bit difference between the classical harmonic oscillator and quantum mechanical harmonic oscillator. So we have done all this thing in our class in your notes. Just focus on this thing and do the previous year question together for all harmonic oscillator problems. Thank you.